Ok, boa tarde a todos. Hoje nós teremos o Dr. Henk como nosso apresentador e o professor Lotuf vai introduzi-lo, porque como eu não conheço, o professor Lotuf o conhece, é o convidado do professor Lotuf. Então, com a palavra, o professor Lotuf, Eduardo pode falar.
Okay. So it's a pleasure for me to introduce Dr. Henk today. We had the chance to meet 2 years ago in a measurement campaign in Netherlands, and then I had the chance to visit him in KNMI, and then we started exchanging, messages, and of course, that he was one of the leaders of the of the Tropomy mission, and which is a spectrometer instrument on board of the Sentinel 5P satellite. Henk got his PhD in 1992 at the University of Groningen. Since 1997, he has been employed as a senior scientist at the Royal Netherlands Meteorological Institute, the famous KNMI. His work focused mainly on composition of the atmosphere. He's an expert on atmospheric chemistry modeling, chemical data assimilation, and satellite observation of trace gases in the atmosphere. Keith, as I said, is one of the leaders of the NO2 product from Tropomi, and he will share with us his experience and maybe his views of the signal over South America and Brazil. So it's a pleasure again to receive you, Henk. It's your words now. Thank you.
Thank you very much. So let me first try to pop up my slides. Okay, let's see if this works. Yeah. So I'm trying to make the full screen now. Can you see it? But I have to go back to the start. Oops. Okay, so you see the slide, I hope. Well, first of all, I would like to express my thanks to Eduardo for inviting me for this talk. As you already mentioned, I have some links with Brazil because my brother, he is living in Brazil, and so I visited Brazil a few years ago to, especially to visit my brother at that time. But I hope to visit again soon, and also maybe to come and visit some of the scientists in Brazil to talk more about science. So my talk today will be about Tropomi, as was already announced. And the title is Air Pollution Monitoring with the Tropomi Spectrometer on the Sentinel 5P satellite. Myself, I'm from the Netherlands, from the institute, the KNMI, which is the Meteorological Institutes of the Netherlands. And what you see here is a map measured with the Tropomi instrument of the NO2 distribution over South America. Okay, but let me start with briefly introducing the department that I work in. That's the Satellite Observations Research and Development Department. And this is sort of a general introduction slide of the department. And one of the big highlights at the moment of the whole department is indeed Tropomi. So our department has Pepijn Veefkind, who is the PI of Tropomi. And we also have Pieter Nel Leeveld, who is the PI of the OMI instrument, which is the predecessor of Tropomi. And apart from these instruments, we have quite a long history in this kind of observations, also with Skiamaki, GOM-1, and the GOM-2 instruments that we are also involved in. Apart from that, we also work on meteorological satellites and especially on wind observations. So that's the Aeolus instrument and EarthCare, but also a whole suite of scatterometers. And the group is basically involved in all the steps. So it's formulating requirements for new satellite missions, planning of missions, design, calibration, then the data processing and the data interpretation. So for Tropomy, Tropomy should be seen as part of this constellation of geostationary and low Earth orbit satellite missions. So Sentinel-5P is sort of a global backbone for a set of geostationary satellites. Over the US, we have Tempo. Over Europe, we have Sentinel-4. And over Asia, we have GEMS. And GEMS has already been launched and is now providing first data sets. Unfortunately, South America is not covered in this constellation, but yeah, so this is really sort of also a backbone for global observations of air pollution from space. Okay, so what I did is I divided my talk in several sections, and I would like to start with showing you the unique features of the Tropomy instrument. So what you see in this slide is Tropomy before it was launched. On the photograph. So you see it's quite a big instrument for a satellite instrument. It's really more than a meter by a meter. And Tropomy was designed to monitor atmospheric composition, basically for air quality, climate change, and the ozone layer. It was launched in 2017, on October 2017. And it's a polar orbiting satellite with an overpass time of 1:30 in the afternoon. What's important to realize is that all the data are freely available and open. And if you're interested in Tropomy, there's two websites here on this slide, tropomi.eu, which is a general access point for Tropomy. And then the data is provided via this Sci-Hub Copernicus EU website. Okay, one unique feature of Tropomy is that it observes the entire Earth in one day. And that's because its swath is really very wide. It's more than 2,000 kilometers, which allows it to really see the entire globe in one day. And Tropomy is measuring a lot of different species. And these are a couple of the operational species that we measure: nitrogen dioxide, ozone, formaldehyde, but also greenhouse gases, methane, and carbon monoxide, sulfur dioxide. So what you see in this graph is sort of a schematic overview of how Tropomy is working. So Tropomy is a spectrometer. It's measuring light which is coming from the sun and which is scattered in the atmosphere. Basically, Tropomy is measuring a full line on the Earth's surface at a given time. And the light coming back from this line or this strip on the surface is gathered in the spectrometer, and then the different colors are disentangled by the spectrometer, by the grating, and this light is then projected on a CCD, a two-dimensional CCD detector, where one dimension is basically the wavelength and the other dimension is the viewing direction or the location on the surface. So this is the way that Tropomy is working. And in fact, the resolution of Tropomy is quite exceptional compared to previous instruments. In fact, Tropomy is called a spectrometer, but it's almost an imaging spectrometer. So it's sort of a hybrid between an imager and a spectrometer, which you can see here. This is 1 day of observations from Tropomy, from a few of the wavelengths to create this false color image of the whole Earth. And you can appreciate the resolution of the instrument. But Tropomy is measuring for each pixel that you see in this plot. It's measuring a full spectrum. It has 4,000 wavelengths that it's observing. And it has bands in the UV, in the near infrared, in the UV visible, and also in the shortwave infrared to derive the different trace gases. And basically that means that Tropomi is providing really a lot of information. So in total, the downlink is of the order of 1 terabyte per day. So it's really a huge data set which is coming down, and quite a challenge to process all this data. So as I mentioned, Tropomi is measuring a lot of different trace gases, and yeah, a lot of them are mentioned here. So ozone, NO2, SO2, formaldehyde, CO, methane, clouds and aerosols. Those are the default products, the operational products. Apart from that, we are also developing more scientific products. So there's things like glyoxal and other compounds which can be derived from Tropomi spectra as well. And here you can see which part of the spectrum the different data sets are coming from. So in my talk, I will focus a lot on the NO2, and this is coming from basically the blue part of the visible spectrum. So a unique feature of Tropomi is the resolution, the spatial resolution. And the interesting thing is that originally Tropomi was designed to give measurements at a resolution of 7 by 7 kilometers. But already before launch, this was improved to 3.5 by 7. And during flight, it was further improved to 3.5 by 5.5 kilometers. So originally, the red box that you see in the image was the foreseen resolution, but now we have the blue boxes as the current resolution. And this is a big step forward compared to previous instruments like, for instance, GOM2 or Skiamaki, which have much bigger pixels. With this resolution, we can really also identify individual big sources of, for instance, nitrogen dioxide. So we can distinguish suburbs of megacities or smaller cities. We can look at individual power plants, industrial complexes, even have a look at highways, the major highway routes, and also the shipping routes can be distinguished in this way. So let me, so the next part is an overview of Tropomi Level 2 data products. So let me start with ozone. So apart from looking at air pollution, Tropomi is also watching the ozone layer. And that's what you can see in the picture on the left, which is 1 day of observations of the ozone layer. In this case, it's the 10th of November, which is quite close after the launch of Tropomi. And yeah, you can see the Arctic ozone hole, which at that moment is sort of disappearing and breaking up. But apart from the stratosphere, we also look at tropospheric ozone, and especially in the tropical zone. So that's one of the products also of the Tropomi instrument, is this tropospheric ozone column. Then Tropomi measures carbon monoxide. And this is an example, it's a monthly mean for January 2020. And you can see that Tropomi is quite sensitive to especially biomass burning and pollution caused by fires. And one thing which you can zoom in now is in Australia. So there were these big fires in January 2020 in the east of Australia, which caused a lot of pollution. And you can see the plumes. But if we now look at one particular day, you can see how Tropomi can map this transport of air pollution, and which is carrying very far. And CO is really a long-lived tracer, so you can follow it really for days before it gets mixed in with the background of the atmosphere. Apart from CO, we also measure sulfur dioxide, and one major source there is volcanoes. So what you see on the left is sort of the continuously outgassing volcanoes, which we can measure. And this is one daily image where you see at least 5 plumes from volcanoes, which have continuous emissions. But really spectacular are the eruptions, and Rijkoke is a very nice example, which I will show on the next slide. So that was really a huge explosion in the north, high north, in the Pacific, where really the ash and the SO2 was deposited into the stratosphere. So the explosion reached very high altitudes. And what you see in the movie, maybe I can play it again, is how Tropomy is following this from day to day. So it's a movie for a period of 3 weeks. And you can appreciate again the resolution and the sensitivity of Tropomy. So it can follow this plume for this period of up to a month. And you can see all the very detailed transport features and the mixing that occurs in the atmosphere. So it's really a great validation data set for detailed tracer transport modeling to see if you can reproduce all these filaments which are happening in the atmosphere. Then we also measure formaldehyde, another important component of air pollution. So formaldehyde is related to the breakdown of hydrocarbons, and formaldehyde has direct emissions from vegetation, especially when you have high temperatures. Then the vegetation starts to produce isoprene, and that breaks down into formaldehyde. So you can see that over really the forested areas in the regions where you have high temperatures. But apart from that, you have a major source, and that's the fires. And what you can see here is a comparison of August and September 2018 on the top with the same months for 2019. And one obvious thing here is clearly the big increase over the Amazonian area and over Brazil in 2019 when you compare that to 2018. So it seems that between these 2 years, there's really an increase in the number of fires that occurred in Brazil. Okay, then also methane is one of the products of Tropomy. And there again, the coverage is really a very unique feature. But with the coverage, we can detect different things. For instance, the emissions from wetlands. If we now zoom into to Africa, in this case, to Nigeria, we can see the delta of the Niger River. And you can see that these wetlands produce quite a lot of methane, which is picked up by Tropomy. And this is another example, the Sud wetlands in Africa, which also are clearly observed by Tropomy. But there's other things which Tropomy can observe. For instance, sudden emissions and especially gas leaks. So this is one that happened in Turkmenistan, which was observed by Tropomy. And this was really also communicated with the government of Turkmenistan, and measures were taken to make sure that this leak was repaired and was no longer seen on the Tropomy images. So Tropomy can really be used for this kind of monitoring as well on a daily basis. Then another important thing of Tropomy is that apart from the trace gases, it also provides aerosol and cloud information. And that's very important for improving the trace gas retrievals. And you can see that on this picture. You can see the cloud cover and also the cloud height images. So Tropomy is also providing a cloud height product. So it's measuring the altitude of the clouds. And then we also have things like the aerosol index, which can be used to identify absorbing aerosols and aerosols in general. which is also important extra information for the trace gas retrievals. Then, yeah, this is especially also the tracking of the plumes is something, because of the daily global coverage that we have, we can really follow plumes and big events in the atmosphere and how the transport of the pollution is happening and where it's going to. So that's quite unique, and you can see that here in the aerosol index. Another product that we have, we can also measure the altitude of the aerosols, the aerosol layer height, and that's what you see on the right here in this image. So we also have an impression of at which altitude the transport takes place. Good, that's the overview as far as all the different products is concerned, but now I will, for the rest of my talk, I will zoom into the NO2 data. So my own task within Tropomy is sort of a final responsibility for the NO2 data product. So that will be the topic for the rest. So why is NO2 important and why would we like to measure it? Well, first of all, for air pollution purposes. So NO and NO2, together with hydrocarbons, form ozone, and that's shown in the image on the right. So you have all these complicated chemical reactions in the atmosphere. But basically, when you combine emissions of hydrocarbons with nitrogen oxides, then you will get ozone. And ozone is bad for health. But NO2 itself also has a direct health effect, so it's anyway good to measure it. And often also NO2 can be seen as an indicator of other pollutants. So often when NO2 is there, you will have other pollutions from combustion processes. Another thing is that NO2 is converted into particles, into nitrates, and that's also harmful clearly for health. Nitrate is deposited, and that's harmful for the ecosystem. That's something which is quite important for the Netherlands at the moment. So fertilization, acidification, those kind of problems are linked to NO2 and NO. And then also climate implications. So they play a role in the formation of tropospheric ozone, which is a greenhouse gas, formation of aerosol, which has an influence on light and on the albedo of the Earth. And it has an impact on the lifetime of methane. So there's many different roles of NO2 in the atmosphere, and clearly a very important gas to quantify accurately. So this is NO2 as observed by Tropomi. It's 1 full year of NO2 data, which I have processed here, and it shows the distribution of NO2 all over the globe. You can really see the pole-to-pole coverage of Tropomi and the very good signal to noise. So you see that over the oceans, you really have this very low noise level, which is really quite fantastic. Even though there is a factor of 100 more or less difference between the highest values that Tropomi is observing and the lowest values. So we can see a lot of different things. For instance, in Europe, we see a lot of signatures from traffic, industry, which are giving these hotspots. In the Middle East, you have a lot of oil and gas activity, which you can observe. We can see shipping lanes on the oceans quite clearly. And if you look carefully, you can even see small shipping lanes in Indonesia. So very thin lines which are popping up there, which is quite fantastic to see. And then we have biomass burning features like over the Amazon and clearly in Africa. But yeah, there's also things like shipping that we can pick up, I mentioned already. So this is a shipping lane over the Mediterranean. It's just a single measurement of Tropomi, single overpass. And you can clearly see the correlation between the high NOx values and the ship positions, which are the circles here. But we cannot only observe the shipping lanes, but a recent paper even showed that that we can observe individual ships. And what is shown on the top left, for instance, is all the ship tracks for individual ships. And underneath you have the Tropomi measurements of NO2. And if we now zoom in to this ship number 6, as it's called in panel B, then you see that that there is a very clear line of high NO2 values. And if you make use of, if you account for the wind speed, then you can see the trajectory of you can predict the trajectory of the smoke plume. And you see that there is really a very good correlation between the smoke plume location that you predict and the amount of NO2 that is measured. So we really observe for the bigger ships, we can observe individual ships and the plumes that are coming from these ships. And the fact is not just one ship, but there's quite a lot of ships that you can detect at the same time. And that's shown in panel C, where we identify, I don't know, maybe 30 ships or so in a single overpass of Tropomi. Then let's go to South America. So I already showed this image on my opening slide. So this is the yearly mean image for South America as observed by Tropomi. And one thing you can do is zoom into the cities, and what you see in the inset is Sao Paulo and Rio and the cities around it, and even the structures of the pollution around the city like Sao Paulo, which is quite detailed, in fact. But apart from looking at the cities, you can clearly also look at what happens in the forests and the fires that are occurring in the forests. And this is the mean result for August of 2018. It's the detailed observations of Tropomi over Brazil. And yeah, you can identify the different spots here where fires occur. And so within a radius of a couple of kilometers, you can identify the location of these fires in this way. This is a year later. And basically what we observe is that the intensity of fires has increased a year later, which is consistent with also the formaldehyde, which I showed before. And especially also in Bolivia, you have these very big fires occurring there in 2019, which didn't occur really in the year before. So in this way, you can really monitor the air pollution, which is coming from these fires over South America. And then you can zoom into the cities also and see the structure of the pollution plume around the cities. So these are two examples for Bolivia, Cochabamba and La Paz, and also Medellin. Medellin is already more difficult to do these yearly means because often there's clouds in these regions. So the statistics is sometimes a bit less, but you can clearly see the sort of the valley structures around Medellin and where the pollution is occurring. Okay, so that sort of gives an overview of the kind of images that you can create with Tropomi for the NO2 measurements. But how does Tropomi measure NO2? So I want to go back to the technique of the measurement. So that's the basic principle is given here. So Tropomi is measuring spectra. And so this is the visible spectrum from red to blue. And if there's no absorption, basically you have a continuous spectrum with continuous intensities. But if there is NO2, so NO2 has a very clear fingerprint, or you could also say barcode. So at very specific wavelengths it absorbs, and in other wavelengths it absorbs much less. And these structures of the NO2 is something which is unique for NO2. And that means that if you observe these kind of stripes, you can be certain that you're dealing with NO2 and not something else. And then if the concentration increases, the lines will become deeper. And so the depth of the lines is a measure of the amount of NO2. But that sounds quite easy, but it's important to realize that the concentration of NO2 is really very low in the atmosphere. So we have 10 to the 9 air molecules for each molecule of NO2. So that's, how can you possibly measure such a small amount? And I'm trying to make you appreciate how Tropomy is doing this by first starting with the spectra that Tropomy is measuring. So Tropomy is measuring directly, it's looking directly at the sun and measuring the solar spectrum. And that's the blue line, which you see in this plot. And it's also measuring down to the Earth and measuring the spectrum which is coming from the atmosphere, and that's the red line. And if you look, for instance, in the middle, so the slope is a bit different, but in the middle you can see that basically these two spectra are almost completely identical. So all the features that you see in the spectrum that you get from the atmosphere, you also see in the sun. And so in lowest order, Tropomy is observing these solar features. So these are solar lines, Fraunhofer lines, which are observed by the satellite. So we have to go a step further. And the next step, what you do is we divide the spectrum that we get from the atmosphere by the spectrum that we measure from the sun. And if you do that, you get this. Basically, you get sort of a straight line almost. But if you look carefully on these lines, so this is the ratio of the two spectra that I showed before. If you look carefully, you will see a little bit of wiggles on top of these lines. And in these wiggles is the information. So what we have to do is we have to blow up these small wiggles. And if we do that, we get this plot. And in fact, we get plot A here. That's the actually measured reflectance from Tropomy. That's the black line A in the middle. And then what we do is we try to simulate this line with the theoretical spectrum that we know from the laboratory. And the theoretical line is line B. And what you can see here and appreciate is that we can describe all these features that we see in line A in quite a lot of detail. And a large part of those features is coming from the NO2. So we, from the depth of these features, we can then derive the amount of NO2. And we can also be certain that we are measuring NO2 and not something else. So it's, but you have to realize that in order to be able to do this, we need an instrument which has a very large signal to noise ratio, because we have to find this one particle into 10 to the 9 air molecules, which is not completely trivial. Okay, so that part is quite clean and works very well, but there are other factors which in fact also cause quite a large uncertainty on the retrieved values that we get, and that's the complexity of the surface, which influences the absolute column amount that we retrieve from the satellite. For instance, you see here the area around the KNMI in the build. And the black areas are basically the forests east of Utrecht. And there are some white patches in there, that's sandy parts. And so there's a lot of variability in the surface properties, which ideally we have to account for accurately to have accurate retrievals. Other complicating factors are the clouds. So that's sort of a second big issue. So we have to characterize the clouds in the retrievals. And we have to account for aerosols in the atmosphere as well, because they have quite a big impact on the scattering properties of the atmosphere. So together, these sort of give uncertainties for individual measurements of the order of 20 to 60%. But another complicating factor is also the vertical profile of NO2, and that also has an important impact on our retrieval. And what we do, in fact, is we don't only do the retrieval, but we run, together with the retrieval, we run a full CTM, chemistry transport model, which tries to simulate all the important processes in the atmosphere, like all the different emission sources, the chemical reactions in the atmosphere, transport in the atmosphere. And another thing that we have to simulate is the stratospheric NO2, because in fact the majority of the NO2 is in the stratosphere. So as first step, we estimate as accurately as possible the stratospheric background, and then we subtract this from the satellite measurement, and we then derive a tropospheric column of NO2. So that's in a nutshell the way that the retrieval works. Important aspects of the retrieval. Now I want to focus on applications of Tropomi NO2. And yeah, I sort of listed different types of applications here in this slide. First of all, a very important aim of an instrument like Tropomi is to do emission estimates. And so that can be inverse modeling, or you can also more directly analyze the plumes or use the divergence method, which I will discuss a bit later. Then identifying sources is an important one, identifying fires, sources which are not known from inventories. That's an important aspect. Data simulation is a very important aim. Especially in Europe, we have this big Copernicus program, which is dealing with Earth monitoring. And part of that is an atmosphere monitoring service, and the comes assimilating Tropomi data and using that to constrain the analysis of the atmosphere and trying to describe the atmosphere in as much detail as possible. Another thing is just direct model validation. Reactive nitrogen is also an important thing, especially in the Netherlands. That's at this moment a very hot topic, because this really has political implications in the Netherlands at the moment. Other things are trend studies, visualization. For the visualization, I already gave you quite a lot of examples, so I think that part is clear. So let me give a few examples of each of these applications. So first of all, estimation of emissions. What people have been doing is analysis of individual plumes. So what you see on the left, sorry, is the city of Paris, and you can see measurements of individual days with Tropomi. And so the top one has sort of a moderate wind speed, and the wind is coming from the northeast, and the plume is growing to the southwest. The second one has a somewhat bigger wind speed and lower concentrations. And the third one is a case where there was almost no wind. And then you can really see this buildup of the pollution in the city. And you can analyze these plumes and use the plumes to get an estimate of the emission. Another approach which is quite neat, which was introduced by Stefan Baerle, is to use to compute fluxes by multiplying concentrations with wind speed, and then calculate divergences. And this divergence is then a direct measure of the emissions. And panel C here shows what you get if you compute the flux divergence. And then you can really clearly identify these power plants, which are around the city of Riyadh in this case, which are the most important sources for that area. But another way is to get emissions is to use inverse modeling and use chemistry transport models with an inverse technique to get emissions. And this is an example from Jiaying Ding. She is also from KNMI, where she estimated emissions and changes in emissions happening during the COVID crisis in China. And all the blue spots are basically strong reductions in emissions that she observed for February of 2020 during the lockdowns that happened there. And another application is to find sources which are unknown. So, for instance, this is a part of Russia where we find this sort of necklace of pearls, if you like, or a string of dots. Which are not, in fact, in the HTAP inventory, which is shown on the bottom right. And if you look with Google Earth and magnify, then you see that every dot here is a compressor station of a big gas pipeline, which is coming from the north of Siberia. And so we can, each of these compressor stations can be clearly identified in the Tropomi measurements. And they have quite a big source, in fact, of NOx in that region. Okay, I already mentioned that CAMS is one of the main users of the Copernicus data, and data simulation is their prime application of the data. So Tropomi data is routinely assimilated, so it's near real-time data, which is assimilated in the forecasting system of CAMS, and is constraining things like carbon monoxide, ozone, and also NO2, hopefully very soon. And then that can be used for air quality forecasts at different scales. And in fact, satellite data can also be used on the regional scale, even at city scales for constraining background values of NO2. Model validation, here's one example that we did ourselves at KNMI. On the left, you see the CAMS regional a priori, or the CAMS regional ensemble. Sorry, on the left, you see the CAMS regional air quality forecasts, which are produced for Europe. And on the right, on the right, you see the model forecast, and on the left, you see the Tropomi measurements. And this is measurements for one day. The gray areas are clouded areas, so there we don't have measurements. But a large part of Europe is cloud-free, and you can appreciate all the details that a single overpass of Tropomi is picking up, and how well these details agree with what the models are providing. So it's really a very nice detailed comparison that you can do on a daily basis in this way. And then I was already mentioning reactive nitrogen, that this is a big issue in Europe, and especially in the Netherlands. And their reactive nitrogen is ammonia together with NO2. And so this has big political implications at the moment in the Netherlands. And in this image, you can see that the sources are really very different for NO2 and for ammonia. So ammonia is mainly agriculture, which is providing the ammonia. And for NO2, it's more the industry and the traffic. And you see that the location of these emissions is very different. Okay, then another topic which is very important is validation. So I would spend just 2 slides on this. So luckily, so Tropomi has this routine validation activity. So on a 3-monthly basis, we get validation reports for all the species of Tropomi, all the operational species. And so that you can find more information on tropomi.eu if you're interested. And this is providing an overview of what we find for NO2. So with NO2, we have at the moment quite an extended network of both MaxDOAs and Pandora stations which provide tropospheric columns or total columns of NO2. And the left plot shows the comparison between MAXDOAS's and the Tropomi data. And what you see there, basically what we observe is that Tropomi has a low bias compared to MAXDOAS at the surface. And other types of measurements that have been done which are very interesting is aircraft mapping observations, so remote sensing aircraft data. And there have been 2 recent papers on this by Judd and by Tak in 2020. And basically what both of these studies find is that there is really a very high correlation between the high resolution aircraft mapping and the Tropomi observations. So that's a very good sign. But also in this case, we find that the slope is not 1, but smaller than 1. So that's something that we are working on at the moment to better understand where these differences come from, and to also improve our retrievals that the slope gets closer to 1. Okay, and that brings me to the last part of my talk, and that's the impact of COVID-19 lockdowns on air pollution. So in the past year, there has been really a massive scientific and also media attention for the Tropomi observations. So I think really millions of people around the world have seen Tropomi data in the past year because it shows so very clearly these impacts of the lockdowns on the pollution levels. And recently I contributed to a review paper which is just published in 2021. It's Katselis et al. In Elementa. And there we reviewed 150 published papers, and that was only until the 1st of October last year. So within half a year, there were already 150 papers on this topic. And it's still growing and continuing to increase. And about 1/3 of those papers made use of satellite data, so about 50 papers. And of that 50 papers, it's mainly Tropomi NO2, which is looked at by the different scientists. So it's really a very popular data set for these kind of studies. And of course, it all started with China. So China went into lockdown around the Chinese New Year. So in February, we had this lockdown. And we could really see this very dramatic change in NO2 levels over China. So on the left, you see sort of the business as usual 2019 values over China. And on the right, you see what happened during the lockdown. And there's really this huge decrease of NO2 happening for a period of about a month. But then China, they sort of had this very strict lockdown, and they controlled the coronavirus very efficiently. And that meant that after a month, they already got back to work. And that's what you see here. So here I compare March, April of 2019 on the left with March, April 2020. And you see that those concentrations are much more comparable. So China is back in business, cars are driving again, factories are working again. And you can see that very clearly from space. Then for Europe, similar kind of big impacts. So what you see on the top is again 2019 as a reference. And in the bottom, you see the lockdown period is basically halfway March, April, where we see reductions in the major cities like Paris, Milan, and Madrid of about 50%. So it's really a huge impact on pollution and a big clearing up of the sky, basically, because of the lockdown measures. This is India, similar thing, even maybe more dramatic. For instance, in Delhi, there was a very strong lockdown. And there was really a very big clearing up of the air, and here we have more than 50% reduction. You can see that very clearly. So on the top you have again 2019 as a reference, where you see Delhi very strongly in the data. But in 2020, the signal from Delhi has almost disappeared. So it's really a very dramatic decrease. This in contrast to the different power plants. So especially in the east of the country, there are very big coal-fired power plants. And some of these power plants were not really reduced in their capacity. So those power plants also do show up with almost the same intensity. But other power plants were powered down, and in many of them we find sort of reductions of 25%. Then we looked at many different cities around the world. So this is Los Angeles, cities in China, Sydney, Mexico, but also South American cities like Lima. Lima showed a very big impact of the lockdown. So we see very strong reductions there. Santiago, Buenos Aires, and yeah. So basically all around the world, you see this big impacts of the lockdowns. Another study that we did in Europe is that we compared this satellite data reductions with reductions that you observe at the surface. And some people are a bit critical about the satellite data, and they say that it doesn't really reflect what's happening really at the surface. But these kind of pictures are sort of quite convincing and show that what is observed as reductions at the surface is quite comparable to what we see from space. So similar sorts of decreases in NO2. Yeah, another aspect which I already stressed a couple of times is the high resolution of Tropomi, and that can be used to distinguish different source sectors. And that's shown in this picture is one example, where in 2019 you can clearly see the emissions from the major highways and also emissions from power plants and industrial complexes. And then the lockdown period showed reductions of all these sectors basically. And you can estimate reductions for the individual. So you can compare reductions of the highways with reductions in the cities and reductions of the different power plants and industrial places. So just because of the resolution, you can do this kind of studies and get much more insight in where reductions come from and what is causing this. And then, of course, with Eduardo, we also had a look at Brazil. And on the top, you see again 2019 as a reference. And then we looked at these lockdown periods, so March, April of 2020, when there was a lockdown, which didn't last very long, apparently. So we could also see a recovery of concentrations later on in April. And that also made the news. So this is from Globo. And don't ask me to translate because I don't know exactly what it meant. What is meant here, but they made some nice pictures of these data sets and showing, yeah, on the left again, 2019 as a reference, the Sao Paulo area, and then this March, April weeks where there were stronger lockdowns and the pollution was really reduced, and then the pollution coming back later on in the month. Okay, that's what I wanted to tell. So let me finalize with my summary. I hope to have convinced you that Tropomi is really a game changer. So it's combining unique features, very high spatial resolution, daily global coverage, very large spectral range with many species that can be retrieved, together with a very high signal to noise ratio, which is, so it's sort of the best of all worlds, if you like. That means that we can retrieve a large number of species Also combined with the information from aerosols in clouds, we can do quantitative retrievals. NO2 is observed over a large range of 2 orders of magnitude, and there again the high signal to noise is a very important aspect that we can do that. I've shown a large range of applications, especially the emission applications are quite important. I stressed the importance of validation, and I also showed that Tropomi is really providing a unique monitoring of the impact of the COVID-19 lockdowns and how that influenced air pollution worldwide. Okay, thank you very much. And I welcome any questions from you.
Many thanks, Henk. It was quite interesting. And now we open for questions. Please, students or people around, do you have any questions? Tem alguma pergunta? You can write.
I have one question. It's me, Eduardo, speaking. Just for curiosity, how do you retrieve the height in the cloud height and the aerosol height with the Tropomi?
Yeah, Tropomi is also measuring in the near infrared, and there you have absorptions of ozone, of oxygen, O2 absorptions, and the depth of those O2 absorptions are basically a measure of the path length of the light through the atmosphere. So if this absorption is very shallow, that basically means that the light was sort of reflected somewhere high in the atmosphere, and if it's deep, then it's low down in the atmosphere. And in this way, we can retrieve heights of both the clouds and the aerosols.
Okay, thank you.
I have also one question that is, I think, similar to that, but it's related to the ozone determination of this 6 kilometers resolution for ozone.
You mean the
you said resolution? That, yes, the 6 kilometer resolution, vertical resolution for ozone.
For the ozone profile, yeah.
Yes.
That's because we measure many different wavelengths. The more you go to the UV, the stronger the ozone absorption becomes. And that means that in the far UV, you will have signals that come from the top of the atmosphere. While if you go more to the visible, then the signal penetrates the light penetrates the atmosphere, and you pick up signals lower in the atmosphere. And so the spectral dependence of the amount of ozone absorption can be translated into a vertical profile of ozone.
Yeah, oh, nice. That's nice. But this cannot be applied for other compounds, no. No, because it depends on this absorption of UV, and then yeah.
No, for instance, for NO2, if you look in total, there is a little bit of height information available, but it's very limited. So it's basically because NO2 has to be derived from a smaller spectral range, and you don't get so much vertical information in NO2. So it's mainly for ozone that you can do this profile retrieval.
Yeah, nice. I have another question. It's related to this. In the south of South America, in this here in this picture you are showing, we have 2 strong signals in Argentina and Chile. Do you know which are the sources for these 2 high emissions? Is
you see Buenos Aires,
yeah,
and Santiago.
And Santiago, okay. Okay, then it's urban emissions now.
Yes, but you also see a clear, I mean, if you look at Chile, you basically see also the corridor south of Santiago. There's a major highway and cities around it. So if you blow it up, you can see much more detail and also pick up other things.
We have a question from YouTube from Sergio. how are the measurements errors over cloudy and polluted cities such as Beijing?
Yeah, so I already mentioned that aerosols are really a complicating factor. The way that we do our retrievals is that we implicitly account for aerosols. That means that from the retrievals, as I mentioned, we get basically from the intensities that we measure, we get two pieces of information. One is the sort of the general albedo, or the amount of reflectivity of the scene that you have, and that's translated into a cloud fraction. But it's also at the same time, it's also an aerosol fraction. So, for instance, if you are over China and it's cloud-free, you will still see a lot of extra reflectivity, which is coming from the aerosol scattering. So that's implicitly accounted for also in our retrievals. And the other thing is what I mentioned is that we use this oxygen absorption to get an impression of the height of the scattering. And that's the second very important parameter that we need. And so that's what we also use to estimate where the scattering occurs in altitude due to the aerosols. But nevertheless, the uncertainties are still quite high. So I mentioned that because of clouds, because of surface albedo effects, and because of aerosols, we still expect uncertainty. So it depends a lot on the scene and on the location, on the solar angle, and yeah. So depends on the circumstances, but typical uncertainties are of the order 30–40%, let's say, of these retrievals. But typically for this image, for instance, what I do is I do a cloud clearance. So those scenes which are really cloud covered are removed from the average, and I look at the low cloud or the cloud-free pixels.
Okay. Yeah, I have another question from Marcia. Marcia.
Hi, Henk. Really nice talk.
Hello. Thank you.
Hi. Yeah, my first question concerns the aerosol correction that you mentioned. Is it similar to the Maxwell retrieval process that you use a continuous function throughout the wavelength, and then you subtract that signal? Because you didn't show the aerosol effect in your slide when you showed the retrieval reservoir of NO2.
Yeah.
No,
what I try to clarify in my previous answer is that the way that we treat the aerosol impact is basically through the generic cloud retrieval that we do. Mm-hmm. So we get these two pieces of information from the Tropomi spectra, which are very important. So it's if you have aerosols, you have a brightening of the scene. So you get more signal from the scene if you have aerosols. But the other effect is that the scattering happens higher up in the atmosphere. And those are the two main effects that you have to describe, and that determine the impact of the aerosols on the NO2 retrieval, on the quantitative amount of NO2. And so we do that effectively through the cloud retrieval. Mm. And in fact, there have been other proposals for retrieval methods that more explicitly make use, for instance, of modeled aerosol distributions. And so there's different ways of doing this, but this is the approach that we are following. So to use as much as possible the information from the satellite itself.
Yeah, probably because also aerosol can absorb radiation, yeah? So
yeah, especially when you really have a lot of black carbon type of aerosol, then things become really messy, and then we have bigger uncertainties.
Yeah, my second question is about the stratospheric concentration on NO2, because you said it's higher. How much higher than you measure in the troposphere? 10 times, 5 times?
Yeah, so the stratosphere is sort of comparable with a lightly polluted tropospheric column, the stratospheric column. But polluted seems, I mean, if you look at this image, it's sort of 80% is sort of unpolluted, huh? Because you have all the oceans, and but the stratosphere is everywhere. So the stratosphere has sort of the Amazonian sort of concentrations are similar to what you observe in the stratosphere, and then you have it everywhere. So in fact, if you average over the whole globe, then the stratosphere is much more than what you have in the troposphere.
Is it possible to see any enhancement in the stratospheric signal? Like, I don't know, pyrocumulus clouds or volcano eruptions, or I don't know, some.
Well, the stratosphere is mainly influenced. Well, the stratosphere has a very strong diurnal cycle.
Okay.
And in fact, you see that in Tropomy, because Tropomy has such a wide swath. That means that the local time of Tropomy is a bit different on the left and on the right. So you have an hour and a half difference in time between left and right. And you can see already the evolution of NO2 in the diurnal cycle evolution by a difference in left and right in Tropomy.
Okay, thank you so much.
See what I mean? So, so this diurnal cycle is very large, but then what's also of concern is dynamical features, and it's transport features in the atmosphere which cause variability in the stratosphere. And the way that we treat this is that I already mentioned that we run, together with our retrieval, we run a full CTM, our TM5 MP CTM that was largely developed in the Netherlands. And the CTM can describe, so it's driven by meteorological analysis, so it can hopefully describe a large part of these features, dynamical variations that occur in the stratosphere, so that they don't interfere with our tropospheric retrievals.
Okay, thank you so much.
Thank you, Marcia. Now, Raquel.
Hi, very nice presentation, very interesting. Thank you for that. You mentioned that you removed the cloud pixels from your analysis. To do that, do you do your own cloud mask, or does Tropomy offers a cloud mask for that, like for all the products, or each product do their own?
Yeah, what we do is it's depending on the product. So, for instance, for methane, it's the cloud mask has to be much more strict. So typically, you remove many more pixels in methane than you do for NO2. So we allow part of the pixel where we measure, we allow part of it to be cloud covered, and we can still do a reasonable retrieval. But Tropomy itself is providing, it's measuring the intensity of the radiation, and the intensity. If you have a measure of, if you have an estimate of the surface albedo at a certain location, you can translate the intensity that you measure with Tropomy. You can translate that into a cloud fraction. And this measured cloud fraction is used for the cloud screening here.
And this cloud fraction is like inside the product, like for the NO2, for example?
Yeah, so the NO2 product that we provide is very extended. So what we try to do is provide full traceability. So all the different elements which go into the retrieval are also in the data file, and that includes the cloud fraction, the cloud height, which is important, but also many other parameters like the surface albedo and yeah, many others.
Okay, no, I'm asking because I'm helping Adolphus. She's here, and her student to look at formaldehyde, and we have to also account for clouds there.
Yeah.
And I'm new to all this
what's
chemistry thing, so I do
right.
the satellite part. The clouds are my specialty, not the chemistry.
Yeah.
So.
But yeah, so Tropomi, all the Tropomi products also have this so-called QA value. And for use of the Tropomi data, basically the first step that you have to do as a user is to filter for the QA value. And for NO2, the cloud clearance, if you want to do that, then basically that translates into a QA value bigger than 0.75. You can also take QA values bigger than 0.5, but then you will also get the good quality cloud-covered pixels.
Yeah, so I assume that for other products are the same, like line of thought. They will have like a quality
yeah, so
flag.
That's something that we introduced for Tropomi, that all the operational products have this QA value, which is used for filtering of the pixels.
Okay, yeah, thank you.
Thank you, Raquel. Eduardo, could you ask talking? It's better because
Sure.
Amy cannot say it.
Okay, I try to put the translation there anyway. Now that Aeolus has some data out there, is somehow the data helping to improve Tropomi retrievals? I mean, is there any kind of data fusion or merging between these two missions? Just out
Sorry,
of
what was the other mission?
Aeolus mission.
Aeolus.
Yes.
So that's, yeah, so the so Aeolus is mainly meant to measure winds, wind
Right.
speeds.
But somehow is that somehow improving the data retrieval, just out of
Yeah,
curiosity.
one interesting application is, of course, what I mentioned is that estimating emissions is basically a combination of the concentrations that we measure with Tropomi with the information about the winds. So if Aeolus can help or to constrain the winds, or can be used to validate the winds that we get from meteorological analyses, that will also help us with the emission estimates. So that's one link, I would say. But Aeolus is also measuring aerosols, and that's also another link. So it can help to characterize the aerosols, and especially the altitude of the aerosols is something which is quite important. And we would like to know if these altitude retrievals work well, and there Aeolus can really help us.
Thank you.
Okay, there is another one here from Laura Klenner. Thanks. The uncertainty of the NO2 varies between 30 and 50% in different parts of the world. How do you determine that number over a given urban area? She asked about uncertainty, or rather bias.
The bias. Well, there's two answers. So what we do in the data product is that we estimate the uncertainties of each individual observation separately, and that will depend on many different aspects, like indeed cloud cover, the surface reflectivity. So is it the dark surface or bright surface that we are looking at? The geometries, so the angles of the sun, and also the profiles in the atmosphere. So it depends on basically all retrieval aspects. So there is this bottom-up estimation of the individual uncertainties of the pixels. And then, of course, then we have our validation campaigns. So we compare our data with the MaxDOAS results, with Pandora's, with SAOS data, and where possible with aircraft data. And that's a very important independent source also to check if our uncertainty estimates are reasonable. I hope that that gives an answer. If you have more detailed questions, I am happy to answer.
Okay, thank you. From Jefferson Soto, there is another question here. What is the role of different emission sources in terms of their contribution to the enhanced concentration levels of NO2 during the high pollution episodes? For example, forest loss hotspots. Just one question. I have to leave. Fatima or Nandulfo, could you take care of the control of this?
Yes, sure.
Okay. Okay, thank you, Henk. I have a question, but it's just curiosity. Yeah, I ask it later. Okay, bye.
Okay, bye-bye. So the question was about the emission.
Yes, what's the role of different emission sources in terms of their contribution to the enhanced concentration levels of NO2 during the high pollution episodes?
During high pollution episodes.
Yes.
Yeah, often it's the meteorology which determines if you have a high pollution episode. So it's if you have very stagnant conditions or very little wind, then yeah, an example here is for Paris, where you see that at high pollution episodes, it's basically when there's no wind. So then the pollution builds up in the city. If you look at Europe, then a lot of the emissions is caused by traffic and by trucks, by cars, also by ships. So that's often something like 50% of the emissions. And then you have various industrial sources, which are quite important for NO2. But in other, if you look at the Amazon, for instance, of course, the fires become very important, and that's also a source which is can give quite big peaks in NO2 if there are major fires occurring, and we pick that up very clearly. And those fires can be of similar magnitude as the biggest cities, or even bigger than that, depending on the size of the fires. So it depends on the location, which is the main pollution, main source of the pollution. Maybe I can go back to one of my first slides, if I can still find it. I think I went too far. No, oops. Where is it? I was too far. Yeah, this one. So this also indicates different sources that happen at different locations. So also the shipping is quite strong, and especially if you have locations where you see a lot of ships. For instance, the Strait of Gibraltar between Spain and Africa. There you can see this big enhancement, which is due to all the ships which are passing through this narrow opening there. So it depends very much on where you are. In the south of Africa, you have this very strong biomass burning peaks, or in Central Africa, I should say. In the south, you have, in South Africa, there are these big coal-fired power plants, which are not cleaned up. So they emit a lot of NOx, and this hotspot over Johannesburg there, that's really dominated by these power plants. So it depends very much on where you are and what's happening.
Thank you. Some other questions? If you want, you can ask in Portuguese, and then we can try to translate. If someone has another question. No? Well, if not, I'd like to thank you. Your presentation was really nice, open for many different questions, and I think it was nice also because then I think we can start using more, and thinking about using more this information.
Yeah.
Yeah, thank you very much. I don't know if Eduardo wants to say something or to.
Yeah, it was very didactic, your talk. We learned a lot. At least I learned many things that I didn't know quite well. And
Yes,
I
true.
thank you again. And I think that many people here somehow want to use Tropomi data, and so that would be a nice case, a nice opportunity now that we know you. And maybe people can send you some messages. I know you're quite busy, but that sometimes there's some doubts about those applications. Okay, thank you again.
Thank you, and I hope you can visit us next time you are here in Brazil. It will be really a pleasure to have you here with us in person.
I hope so too. Yeah.
Yes,
would be really nice.
Yeah.
That would be my idea. If I find a good opportunity to come to South America, I would like to visit some of the science teams also, and that would be a nice opportunity. Well, from my side, thanks a lot for the invitation, and it was really a pleasure to present this colloquium for me and to get all your feedback. And please, if you have any specific questions on the data set, you can send me an email, and hope to find the time to answer.
Yes, thank you very much, and have a nice weekend. Nice weekend for everybody. Bom final de semana e obrigada a todos.
Obrigado, Fátima. Thank you, everybody. Obrigado a todo mundo aí por participar.
Tchau, tchau. Obrigada.
Okay.
Okay. Bye, bye.
Everyone.
Bye, bye.
Bye.